Lesson 40 is the most important lesson for this unit, so we'll spend a couple of lessons on a couple of videos on this lesson, the conservation of energy, which basically says that energy is always conserved. And the lesson starts off by talking about mechanical energy. What is mechanical energy? Mechanical energy is the total of kinetic energy and potential energy. So in this first example, we've got an airplane flying at this altitude at that speed, and we want to determine the total mechanical energy. And just to get ahead in the lesson a little bit, conservation of energy says if the plane has this amount of mechanical energy at this given point, let's say if I turn off the engines, for example, and the plane starts to plummet towards the ground, it will always have that amount of mechanical energy. So as it plummets towards the ground, its velocity is going to increase, therefore its kinetic energy will increase, but its potential energy will be less because it's closer to the ground. But if you add those together, they will always equal the same amounts of mechanical energy. So the first thing we need to do is calculate how much mechanical energy does that plane have. And the formula is right here for us, a different color. It simply is the mechanical energy equals the kinetic energy plus the potential energy. From our previous lessons, we've learned that the kinetic energy is 1/2 mv squared. The potential energy is mgh, and in this question, it's just a matter of plugging in the numbers. Make sure you convert kilometers per hour to meters per second. See, and we get the 14,300. You can factor the m out if you want, but probably more hassle than it's worth. 214. Don't forget to divide that by 3.6. And don't forget to square it. Oh, we're going to run out of space, so mg. Note that it's just a positive 9.81 because energy is a scalar quantity, so I don't need, or I don't want to put the negative in there. If I put it in there, the negative in there, I'm going to get the incorrect answer. Plug that into your calculator, and you are going to end up getting, oh, you're going to get 0.5 times 14,300 times bracket 214 divided by 3.6 and the bracket squared equals plus 14.3 times 9.81 times 497 and the bracket. Ooh, you end up getting 9. What number is that? 1, 2, 7. 9.5. 1, 2, 3, 4, 5, 6, 7. Yes. 9.5 times 10 to the 7 joules. We're talking about an airplane. We're talking about something with a fairly great amount of mass and at a high altitude flying at a great velocity. So of course this thing is going to have a lot of mechanical energy. So this number here, mechanical energy, the plane will always have that amount of mechanical energy. Now that's assuming you don't add any more energy into the system. So for example, if the pilot presses the throttle, puts more fuel into the engines and the plane goes faster, then yes, the mechanical energy is going to change. But as I said, if the plane starts, the engines go off and the plane starts going towards the ground, it's always going to have that amount of mechanical energy. Onward. So the next part of the lesson talks about types of systems. And we are only, in Physics 20 and 30, we're only going to be dealing with one type of system, and that is this one here, an isolated system. And in an isolated system, matter is conserved and energy is conserved. When you get into university physics, you'll talk about closed systems and open systems where things are not necessarily conserved. But for the purpose of Physics 20 and 30, energy and matter are always conserved. So we only need to worry about isolated systems. And here is conservation of energy right here. The mechanical energy before equals mechanical energy after. And as stated, this is known as the law of conservation of energy. It's a pretty important law for physics 20 and physics 30. And here's our classic example. We're sitting on a toboggan at the top of the hill. We have this amount of mass. Determine how fast you will be going when you reach the bottom of the hill. So here's the hill. Here at the top of the hill, on your toboggan, you have, what kind of energy do you have at the top of the hill? Well, at the top of the hill, assuming you're just sitting there, getting ready to go, you are all potential energy. And when you get down to the bottom of the hill, you are all kinetic energy and no potential energy. So here, the EK is, the EP is a max, and the EK at the top, assuming you're just getting ready to go, is 0. At the bottom, the EK is the max, and the EP is 0. And anywhere in between, like right there, for example, then you're going to have some of it's going to be EP and some of it's going to be EK, but they're always going to add up to the total mechanical energy before the situation, before you started going down the hill. So let's do this as described. EM equals EM prime. The mechanical energy before equals the mechanical energy after. EP plus EK. EP prime plus EK prime. And as you can see, because we've done this diagram and labeled some things, you can see what's going to happen. At the top of the hill, the EK is 0. So really, this is just EP plus 0. And at the bottom of the hill, the EP becomes 0 because now you're on the ground, you have no height. And the EK is a max. So we can just change this to MGH. We can change this to 1/2 mv squared. And what are we solving for here? We are asking for the velocity. The velocity. And note, well, what interesting thing happens that you may have guessed was going to happen. In this specific case, just like if you recall circular motion, the mass cancels out. So the mass is irrelevant in this problem. In this specific problem, it is irrelevant. Just like when we did circular motion and you had to calculate the minimum velocity that something can go around in a vertical circle without like a roller coaster falling off the track, or spinning something with a string without so the item stays going in a full circle. The mass was irrelevant in those specific cases. In this specific case, the mass is also irrelevant. And we can just rearrange this and solve for V. V equals 2GH square root. And then you can plug those numbers in. 2 times gravity times the height. 2 times 9.81 times the height, which is 23.7 equals, and the square root of that number is 21.6 meters per second. Which seems like a pretty reasonable velocity for a toboggan. Now that assumes there's no friction. In real life, if you're going down a hill on a toboggan, you're not going to be going at 21.6 because there is definitely some friction. I mean, you might be going close to that depending on the condition of the snow. All right, onward. Example number 3 is the classic Wile E. Coyote problem. And it's similar to the problem we've just done, except for this time, we are going to calculate the velocity at the top. Oh no, not at the top. Yes, at the top. And then at various points during its fall, and then at the bottom. So here's the mass is 200 kilograms of this boulder, and it's going to fall to the bottom. It's going to fall a distance of 45 meters, and we want to calculate the velocity at 45 meters, and we want to calculate the velocity at 30 meters, at 10 meters, and at 0 meters. So let's just talk about that briefly. Obviously, at 45 meters, we assume that the boulder is not moving yet, so its velocity is going to be 0. And at the bottom, at 0 meters, it's going to be a maximum velocity. At 30 and 10, it's going to be somewhere in between in between 0 and the maximum velocity. So A is easy. A, you don't even have to do any work for that. You can just say at A, it's 0. However, what we are going to do for A is we are going to calculate the mechanical energy of the boulder. Because remember, the mechanical energy stays constant no matter what point above the ground it is. So let's just calculate the mechanical energy. And the mechanical energy, in this case, since it's not moving, it has no kinetic energy, is very simply the potential energy, mgh and that gives us a value of 88,290. Let's remember, that's the mechanical energy, and no matter where the boulder is, it will always have that much mechanical energy. And knowing that is going to enable us to calculate the velocity much faster than if we just repeat this whole process every time. So now we can start doing the other questions. B is when it's at a height of 30 meters. So we know that the mechanical energy always equals the potential energy plus the kinetic energy. And what are we solving for here? We want to know the velocity. The velocity, let's plug in the numbers right away, because we automatically know that the mechanical energy is 88,290. We know that the potential energy is going to be mgh. What was the m? The mass, 200. G, once again, there's no negative because energy is a scalar quantity. And this time, now it's at a height of 30 meters above the ground, plus 1/2 times the mass times the velocity squared. We're solving for the velocity squared here. So in this example, I just plugged in the numbers. I'm going to solve for the velocity. You could have rearranged the formula if you want. I just don't think it's necessary in this specific example. So then you can multiply those numbers together. Let's do that. 200 times 9.81 times 30 equals 58,860 plus 1/2 times 200 is 100 v squared. Subtract this number from both sides, or move it over to this side. So 88,290 minus 58,860 equals 2,943 equals 100 v squared. Divide by 100 and take the square root. And you get the velocity is 17.2 meters per second. Sounds pretty reasonable. So there is B. For C, it's going to be exactly the same as what we did in this question, except for now you replace the 10, replace the 30 right here with 10. And if you do that, now obviously it's going to be going faster. Why is that going to work out to be a bigger number? Because when you multiply this, when this changes to 10, this number becomes smaller, and then when you subtract it from this number, you're going to get a bigger number right here. And anyway, I'll let you do that I think you can probably handle C by yourself. It's exactly the same as B, except for replace this with 10, and you end up getting a velocity of 26 meters per second. And for D is actually one of the easier questions, simply because all the mechanical energy, all the potential energy has been converted into kinetic energy. So we can just say that mechanical energy equals the kinetic energy, or 88,290 equals 1/2 times the mass times the velocity squared, and solve for the velocity in this one, and you end up getting an answer of 30 meters per second. So that's a basic conservation of energy question. We've got a few more examples that we're going to go over in the next lesson.